Got that going. So let's try to do first do a quick recap of what we talked about last time, quick review. Last time a lot of the class was proving that a bunch of languages were decidable. We proved a bunch of languages were decidable. So first language we talked about was, we call it the acceptance problem for DFAs. The acceptance problem for DFAs. Now what is that? It's the set of all encodings of a DFA and some input string such that that DFA D accepts the input string W. So just to give you a random example, here's a random DFA, here's its start state, here's its accept state. On a 1 we go there, on a 1 we go back, on a 0 we loop to ourselves, on a 0 we loop to ourselves. What's a string that accepts? This accepts any string that has an odd number of 1, so that would accept the string 1, 0, 0, 0, 1, 1. So D would be the encoding of this. Remember, this has a proper definition. We can write it out as a bunch of symbols. So the encoding of this machine D, together with this string, would be in this set. That's one of the things in there. Because this machine, D, accepts this string. This exact same machine, again with this string, would also be in there. This machine with this string would not be in there. So, it is the set of every possible DFA and every possible input string such that that DFA will accept that input string. That make sense?
Every possible DFA?
Every single one in existence.
So it includes every string in existence?
Every string in existence that will ultimately be accepted by a DFA.
Okay.
Yes.
So W has to be something that is accepted, because your words say accepting is decidable.
So the set of all encodings of D and W, where D is a DFA accepting string W.
Oh, okay.
This language, and there's my M parenthesis, or M bracket, is a decidable language.
Oh, okay, I missed that last one.
Okay.
That makes sense.
So that's what we're saying. We're saying that we call that the acceptance problem for DFAs. We proved that the acceptance problem for DFAs was decidable. We showed how to construct a Turing machine that decided this language. It would say yes every time you gave it an encoding that was in this language, and it would say no every time you gave it an encoding that wasn't in the language. We did that last time. We also did the acceptance problems for NFAs. Exact same thing, except for we switch out D with N, where N's an NFA. And we showed that that was decidable. We also showed that the acceptance problem for regular expressions was decidable. If you give, it's possible to construct a Turing machine such that you give it a regular expression and some string, and it answers yes, that regular expression can generate that string, or no, that regular expression cannot generate that string. That's a possible algorithm to make.
What's a regular expression again?
A regular expression is anything that we do with our regular operators. Our regular operators were, what were they? Star, concatenation, and union. So here's an example of a regular expression. Any expression you can make using stars.
Oh, those are zeros and ones, okay.
Oh, yeah, those are zeros and ones. Concatenation, we didn't usually write that symbol. We just put next. But 1, 0, 1, 1.
Okay.
So you do this or that, are all the regular expression, or all the strings that this regular expression generates.
And there are like 3, I think?
There were 3 operations.
Okay.
Yep, star, union, and concatenation.
What about intersect?
Intersect was not a regular operation. Or sorry, intersect was not a regular expression operation.
Okay.
So it's just those 3. But we already proved that regular expressions are logically equivalent to DFAs. And we went over how to convert a regular expression to a DFA. So if we can do it for DFAs, and every regular expression can be converted to a DFA, we can do it for every regular expression. That was the thinking there. We also did the emptiness problem for DFAs. What's the emptiness problem for DFAs? So the emptiness problem for DFAs is a set of all DFAs D's, all DFAs D, such that the language of D is nothing. So it's possible to build a Turing machine, it's possible to come up with an algorithm that you give it a DFA and it says, yes, that DFA's language is empty, or no, that DFA's language is not empty. And we went over how to do that last time. Is it starting to come back to you?
To a degree.
We also did the equality problem for DFAs. What was that? If you gave it two DFAs, it could tell you, yes, they have the exact same language, or no, they do not have the exact same language. We also showed that was decidable. We showed that the acceptance problem for context-free grammars was decidable. You give me a context-free grammar and a string, I can tell you, yes, that string is generated by that context-free grammar, or no, that string is not generated by that context-free grammar.
I also forgot what context-free grammar was.
Well, remember what a grammar looks like, something like S goes to A, B goes to A or 0, A goes to 1, or the empty string, something like that. And you apply the rules to ultimately get a string.
Yeah, I'm seeing.
If you get a string, then it was generated by the grammar. Okay, so we showed that was decidable. We showed the emptiness problem for context-free grammars was decidable. In fact, we showed every context-free language, which is any language that can be generated by context-free grammar, was decidable. So we proved lots and lots of things were decidable. And then we came across the acceptance problems now for Turing machines. What's the acceptance problem for Turing machines? The acceptance problem for Turing machines is a set of all encodings of M and some string W, where M is a Turing machine that accepts W. We started looking at this problem, and we started our argument to say that this is undecidable. It is not decidable. So the way that we proved all these things were decidable is we just came up with a Turing machine that could do it. If a Turing machine could decide them, then they're decidable. Now we start our argument for this thing is undecidable. There is no Turing machine that can do it. That's a different kind of argument. It's a very weird kind of argument to have to make. So the whole crux of the next section that we're going over is making sure that you understand how this is true. Okay?
You said that all of the one above are decidable because a Turing machine can make, you can prove through a Turing machine.
All these are decidable because I can come up with a Turing machine that shows it.
And now you're saying Turing machines are undecidable.
Now I'm saying the acceptance problems for Turing machines is undecidable. It is impossible for you to come up with a Turing machine such that I give you a Turing machine and a string and say, does this Turing machine accept this string? And your Turing machine, your algorithm, concludes yes or no.
Yeah.
That's what we're going to show is impossible, which is kind of weird. So that's the crux of what we're trying to show. And then we're going to go off on some weird tangents and then come back to it. One more thing that we talked about last time that is going to be important for you to know, jumping back into these proofs, is a definition of what it meant for two sets to be the same size. Remember what it meant for two sets to be the same size? How do I know that the cardinality of A is equal to the cardinality of B if they're both sets?
Has to do with infinity and things like that.
Well, we argue about infinite sets using the definition. But how do I know if two sets are the same size? You know the naive way to do it, count them.
Yeah.
I count everything in A, I count everything in B, and we know that they're the same size. But turns out you're doing too much work. You're overworking yourself. Go into a crowded room full of people, right? Crowded room full of people, no one in the room's deformed. And I ask you, are there the same number of right hands in that room as there are left hands in the room? Yes.
Yeah.
How many right hands are there? No clue. How many left hands are there? No clue. And yet you know that there's the same number. How do you know that there's the same number?
Because everyone has two. One of each.
Because for every right hand you have, you know that there's a corresponding left hand to go with it. So you don't have to count to know that two sets are the same size. Instead, if there's a way that you could map off all the hands together, you could instantly know. If you could pair them all off, you could say this hand goes to this hand, this hand goes to this hand. That kind of pairing with a function we call a bijection. So we know that the set A has the same size as the set B, if and only if there exists some function from A to B such that f is a bijection. Or in other words, f is 1 to 1 and on 2. These properties coming back to you? We kind of flushed over them last time. What does 1 to 1 mean, roughly?
That all of the outputs have one input.
Yeah, for every one thing in B, only one thing in A maps to it. So if we think about B as our set of right hands, and A as our set of left hands, 1 to 1 means, for every, first off, the fact that it's a function means we're mapping every left hand to only one right hand. That's how we know it's a function. The fact that it's a 1 to 1 function means every right hand only gets one left hand mapped to it. That's 1 to 1. So we're pairing them off exactly, 1 goes to 1. On 2 means that we use all the right hands. So there's no one deformed. We can't have some deformed person who only has a right hand and no left hand to go with it. Otherwise our function would no longer be on 2. There'd be a right hand that didn't get mapped to.
Good.
If a person had a left hand and no right hand, then it's not a function because we didn't map the left hand to anything. If they had a right hand and no left hand, then our function is not on 2 because we have to use all of B. That's on 2. This coming back? All right. Quick example. Just make sure it's super clear. A is a set 1, 2, 3. B is a set A, B, C. Are these sets the exact same size? Yes. How can we prove it? We create a function from A to B that's 1 to 1 and on 2. So here's F. It maps 1 to A, 2 to B, 3 to C. There's our function. Is it on 2? Did we use all of B? Yes. There's A, there's B, there's C. We used all of B. Is it 1 to 1? Yes, because only one thing's mapping to A, only one thing's mapping to B, only one thing's mapping to C. So it's 1 to 1, it's on 2, therefore it's a bijection. Therefore I know that these two sets are the same size. Sorry, just a bracket there. Alright, now let's do a different proof. We didn't do this one last time, so decide we do a different one from what we did last time just to try and get you comfortable with this. We're going to prove that the natural numbers and the integers are the same size. Kind of weird. What are the natural numbers? 0, 1, 2, 3, 4, 5, 6. What are the integers? 0, 1, 2, 3, 4, 5, 6, plus negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. Shouldn't there be twice as many integers as our natural numbers? Kind of weird. No, there's actually the exact same many. They have the same cardinality. How do we prove that? We need to come up with a bijection between the two. I need to prove that's a bijection. So let f be the function that maps the natural numbers to the integers by f of n is equal to n over 2 if n is even, and negative n plus 1 over 2 if n is odd. Let's get a feel for how this function maps. We'll do n up here and f of n down here. So the things that we're going to plug into the function are the natural numbers. Here's our domain. So we're going to plug into this function 0, 1, 2, 3, 4, 5, 6, etc. Right? What's going to come out of the function? Well, let's test it. When I plug 0 into this function, what do I get? 0 is even or odd? It's even, so we use this one. What's 0 divided by 2?
0.
0. So 0 maps to 0. Okay, now we plug 1 in. Is 1 even or odd? It's odd. So we plug it in down here. 1 plus 1 is?
2.
Divided by 2 is?
1.
Make it negative. So 1 went to negative 1. Okay, plug in 2. 2 is even. 2 divided by 2 is 1. So 2 goes to 1. Plug in 3. 3 is odd. 3 plus 1 is 4. Divided by 2 is 2. Make it negative. Negative 2. 4. 4 is even, so we plug it up here. 4 divided by 2 is 2. And 5 is going to go to negative 3. 6 is going to go to 3, etc. And every integer is eventually going to get mapped to. Now, we still need to prove that, but hopefully you have good intuition right now for this is a bijection. This is going to map every single natural number to only one integer, and every integer is going to get mapped to. So, now let's prove that. So here's our function. I need to prove that this thing's a bijection. How do I prove it's a bijection? I prove it's 1 to 1 and on 2. Right? How do we prove a function's 1 to 1?
That every output only has one input.
If the outputs are equal, the inputs are equal. Forcing the discrete math students to remember this. If the outputs are equal, then the inputs are equal. So let x and y be natural numbers such that their outputs are equal. So x and y are elements in the domain such that their outputs are equal. And observe that f of x has to be greater than or equal to 0, or f of x has to be less than 0. Those are the only two options. Right? So, if f of x is greater than or equal to 0, then x over 2, that means that it came from this. Because all these ones are negative. These ones are going to be greater than or equal to 0. So if f of x is greater than or equal to 0, I know f of x is equal to x over 2. But I also know f of x is equal to f of y. And I know f of y must also be greater than or equal to 2, so f of y is equal to y over 2. So I get x over 2 is equal to y over 2, or in other words, x is equal to y, or in other words, f is 1 to 1. If the outputs were equal, I just really showed that the inputs are equal. Right? Similarly, we just found the case if f of x is greater than or equal to 0, but we're going to do a similar thing if it's less than 0. If f of x is less than 0, then I know f of x is equal to negative x plus 1 over 2, and I know f of y is equal to negative y plus 1 over 2. So I know that these two things are equal. Multiply both those by negative 2, and you get x plus 1 is equal to y plus 1. Subtract 1 from both sides, you get x is equal to y. Therefore, either way, f is 1 to 1. Shorthand for 1 to 1. 1 dash 1, 1 to 1. We don't like spelling it out over and over again. Okay, so we showed that in either case our function is for sure 1 to 1. Now I need to show that my function is onto. What does it mean for my function to be onto? It means we will eventually map to every integer. It means if we followed out this pattern, we would eventually list whatever integer you have in mind. So you pick any integer out here, z, and I may prove to you that we will eventually map to that integer z. So let z be any integer, and observe that z is greater than or equal to 0, or z is less than 0. Those are the only two options for an integer. Right? Now I'm looking for something that maps to z. That would show that we eventually map to z. So if z is greater than or equal to 0, then z is equal to 2z over 2, which is equal to f of 2z. What's f of 2z? 2 times an integer is even. So we're using this one. So 2z over 2, which is just z. So 2z over 2 is a natural number. Therefore, it's in the image of f. So I just barely showed we'll eventually map to it. What's the thing that maps to z? 2z.
If it's positive.
Yeah, if it's positive. So if you pick some integer, give me a positive integer. 5, 10 is going to be a thing that maps to 5. You pick 200, 400 is going to be a thing that maps to 200. That's what we showed. Okay, now what about if it's negative? If z were less than 0, notice here, here's a weird piece of logic, but hopefully you get it. Z is less than 0. Z is a negative number. So negative 2 times z is a positive number. And what is the smallest negative 2 times z can be?
0.
No.
Oh.
Z is less than 0. So the smallest negative 2 times z can be is 2. Right? And that's when z is negative 1. If z is negative 1, negative 2 times negative 1 is 2. If z were negative 5, negative 2 times negative 5 would be 10. So the thing that makes negative 2z the smallest is when z is negative 1. So the smallest negative 2 times z can be is 2. 2 minus 1 is 1. So the smallest this whole thing can be is 1, which is greater than 0. So bit to follow there, but so negative 2z minus 1 is for sure greater than 0. And also notice that it's odd, because negative 2 times z is going to be even. 1 away from an even is always odd. I'm not going to argue the odd too rigorously there. Hopefully you follow that. So this is an odd, and it's greater than 0. Or in other words, this is an odd natural number. Okay, so then when we plug it into f, when I plug negative 2z minus 1 into f, we use this function down here, because it's an odd natural number. And f of negative 2z minus 1, plug that in for n, so we have negative n plus 1 over 2. You follow that? A bit ugly, but we're just plugging in for n up there. Negative 1 and positive 1 cancel out, leaving us negative 2z over 2.
Oh, yeah.
Negatives cancel out, 2's cancel out, and we're left with just z.
Huh, interesting.
So here is a natural number that will always give you z. So pick any negative number z.
Negative 6.
Negative 6. So negative 2 times negative 6 is?
Negative, or is positive 12.
Minus 1 is?
11.
So 11 would have been the thing that mapped to negative 6. So I just barely showed for any integer you pick, I can find the natural number that will ultimately map to that integer. Therefore, your integer that you chose will eventually be mapped to. Or in other words, we will eventually map to every integer. Or in other words, our function maps to all of z. Or in other words, our function is on 2. So our function is 1 to 1, our function is on 2. That's the definition of a bijection. So f is a bijection. Therefore, the size of n is the same as the size of z. What does it mean for two sets to be the same size? You can create a bijection between them. That's the definition of what it means for them to be the same. We don't say size, we say cardinality, but same thinking.
And they have to, okay, so if you have the same input, you get the same exact output. The output could be the same from a different input.
No, not if it's 1 to 1. If the function's 1 to 1, then if inputting the number 1 spits out 6, no other number can spit out 6. Otherwise, it's not 1 to 1.
Could it be 1 to 1 by coincidence?
Well, if it's 1 to 1 by coincidence or not, either it's 1 to 1 or it's not. And if a function is 1 to 1 and it's on 2, it's a bijection.
Okay.
So an example of a function that's obviously not 1 to 1, think about a mod 2 function for programming. You have a function that just mods your integer by 2. Half the numbers it's going to spell 1, half the numbers it's going to spell 0. That is not 1 to 1, because a lot of numbers are mapping to 0 and a lot of numbers are mapping to 1. Now, imagine you program the +1 function. It takes an integer and it just adds 1 to it. Now that function is 1 to 1, because the only thing that will ever spell 6 is 5. We are not moving that yet. We're still here. Okay. Any more questions about this? I know it's a bit dense, giving you the full-blown proof instead of just the idea, but figured why not.
That was awesome.
All right. Okay. Now, last time we went over an argument showing how the rationals were also the same size as the integers. Were also the same size as the naturals. And we used the dovetailing method, if you remember that.
Oh,
Not going to re-go over that, but just to remind you, last time we already concluded that all three of these things were the exact same size. Since last time I linked these two together, this time I thought I might prove those two go together. Okay, now here's the last thing we proved last time, and I told you that we'd start by reproving this, but then decided we should probably back up a bit. So, now what are we going to prove? We're going to prove that the real numbers is uncountable. Terminology really quick. If your cardinality is the same size as the natural numbers, or smaller, then we call you countable. So the set 1, 2, 3, the set containing 1, 2, 3, is countable. Every finite set is countable. Similarly, the natural numbers is countable, the size or the integers are countable, and the rationals are countable. Kind of weird that the rationals are countable.
yeah.
Remember how weird that is? Because between any two integers, 1 and 2, how many rationals are between 1 and 2?
Infinite.
An infinite number. So just between two integers, there's an infinite number of rationals, and yet, there's the same number of rationals as there are integers. Very strange. Very unintuitive. Now, you would think, okay, so the reals are probably the same as the rationals. But no. The reals are a whole new beast. It is impossible to create a bijection from the naturals to the reals, and that's what we're going to prove. That's what we mean by the reals are uncountable. We mean that you cannot create a bijection from the naturals to the reals. That's impossible. Now, in fact, we're not even going to use all the reals. Kind of makes our proof messy. We're just going to use the reals between 0 and 1.
You could use it, I mean, infinitely small range and it was still.
Yes, we could use all the reals between 0 and point 0.00000001, and it would still work. But we'll use between 0 and 1 because that makes the proof the easiest to read. Okay, so we're going to show that the real numbers are uncountable. And in fact, what we're going to show is that the real numbers between 0 and 1, which is just an arbitrarily small subset of the real numbers, not arbitrarily small, but you'd think that this is infinitely smaller than this, right? Although this is actually the same size as that. That's a proof for real analysis. Anyways, we're going to show that just the subset 0 to 1 is uncountable. All the real numbers between 0 and 1. That's what this is shorthand for. Okay, how are we going to prove this? We're going to prove it's impossible to create a bijection from the natural numbers to this. So we assume by way of contradiction that the open interval 0 to 1 is countable. What does it mean for it to be countable? It means that there exists some function f from the naturals to that interval such that f is a bijection.
Yeah.
We are going to show that f is not on 2. Since it's not on 2, it's not a bijection. So we lied. So assume by way of contradiction that f is a bijection, or in other words, that implies f is on 2. And then we're going to show f is not on 2. You with me? Here's the way that we're going to do that. We're going to construct some new number x. We're going to start out with x is 0 point, and then we're going to look at our first number and look at its first decimal place. Whatever that decimal is, for the first number it's 8, we're going to put a 9 here. We're going to put that decimal plus 1. Our second number here, its second decimal, is a 9. 9, we can't plus 1 to that decimal, so when we see a 9, we're just going to replace it with an 8. For our third decimal, we look at the third number. Its third decimal is a 1, add 1 to that, we get 2. For our fourth number, its fourth decimal is a 4, we add 1 to that, we get 5. Our fifth decimal, or our fifth number, its fifth decimal is a 5, we replace that with a 6. This one, we replace 9 with an 8, and we didn't need that one because we're out of space. You with me? Yeah. Alright. X now is going to be different from this number for sure, because they differ in their first decimal place. X is going to be different from this number for sure, because they differ in their second decimal place. They differ in their third. They differ in their fourth. They differ in their fifth. They differ in their sixth. And I generate x all the way. It's an infinite decimal expansion. And it's going to be different from every single one of these numbers. That's the idea here. So construct x in the closed or in the open interval 0 to 1 such that x is nth. That's not part of it. Such that x's nth decimal is 8 if f of n's, the one at that location's nth decimal is 9, and one more than f of n's nth decimal otherwise.
Why did we use 8, not 0? Is there a reason?
We could have replaced 9 with 0 and it would have been fine. It's arbitrary. So then, for every natural number in n, f of n is not equal to x, since they differ in their nth decimal place. Therefore, x is not in the image of f, which means f is not on 2. Contradiction, because we assumed f was on 2. Therefore, no such f can exist.
It's tricky.
So if you can't create any bijection, then that means that the set is uncountable. Because if it were countable, we could create the bijection. We proved that you can't. So it is uncountable. Yeah, it's a little bit weird doing proofs with infinities like this.
Is there like a way to, I get it not bijection, but you would be like, it's the size squared or something like that to be able to.
Now you can't square an infinity.
Why not?
Because infinity is not a real number.
Okay, why is that? Well, I don't know, maybe it's not a different subject. But.
Well, squaring is a shorthand for taking a number and multiplying it by itself. Multiplication is an operation on the real numbers. Infinity is not a real number.
You can't multiply infinity.
So you can't.
So it doesn't make sense to multiply infinity by infinity.
Why not?
Multiplication is something we do with real numbers.
Why?
The same way I can't take desk multiplied by globe. Desk and globe aren't real numbers. Now we do have a notion that's kind of like infinity that we work with called a limit in calculus. And it's kind of like you're working with infinities, but that's a calculus concept.
Is this proven or is it just accepted?
It's proven. I can rigorously tell you that's a good thing. You can completely understand how we work with infinities in calculus. It's all rigorously proven. The definition of a limit is 100% rigorously proven. And
So you can't square a complex number.
you can square a complex number. That's also an operation. We know what it means to multiply a complex number by a complex number.
Even though.
And it's well defined. And we define it in terms of the real numbers.
So infinity is not a complex number.
No, infinity is not a complex number. Infinity is not a real number. We put it as it's what we call an extended real number.
Why do we compare things like size, which is an actual number, with terms?
Is size an actual number?
Apparently not in infinity.
Apparently
because
not.
The size of.
Apparently you don't need some actual number to see that two sizes are the same, or two sets are the same size.
But you could also say that any number is, or infinity is greater than any number.
We use infinity as a notion for something arbitrarily large. Yes.
So.
Oh, we didn't do that last proof.
So you're saying that we use it that way, but that's actually not what infinity's meant for. It's like an improper way of using it.
It's an okay way of using it for something arbitrarily large. It's not a real number. We often think about it as a value greater than any real number. That's infinity. But there is no greatest real number. You can't say infinity is the biggest number.
You can't?
No. Because any real number plus 1 is bigger than the number itself. X plus 1 is always greater than x. And so if you said infinity is a real number, then infinity plus 1 is bigger than infinity.
So what is it? Just break our math, and that's why we don't use it?
No, it's said it's not a real number. A real number, we're getting into the foundations of real analysis. The same way that you ever do geometry and look at the postulates of geometry, the axioms of geometry, or maybe in your class with the Brother Kai that you're doing, you probably came across like the axioms of arithmetic. You ever go over that?
But I can't quite remember it. I mean, I'm sure I know it the minute you mention it, maybe.
Well, one of the axioms of arithmetic, for example, is that when you addition is commutative. A plus B is equal to B plus A.
Yes.
It's not something you prove. It's an axiom.
Okay. So is this also an axiom?
No, what is an axiom in real analysis that makes like you can start working with the concept infinity is called, we call it the completeness axiom. And it says that any subset of real numbers bounded from above has a least upper bound. And how that gives you infinities is no way intuitive, but that's the axiom that does it. And so if you assume that any set of real numbers bounded from above has a least upper bound, then it turns out that's the concept you need to ultimately start defining limits, which is what we use to talk about what you have intuition for when you say infinity. Arbitrarily big and arbitrarily small.
Okay, let's let it rest for now.
Yeah, real analysis, I mean, it's not something that you just have a quick conversation about and now you get real analysis.
Yeah.
It's known as one of the most difficult areas of mathematics to understand.
I'll just accept that I don't know it.
Well, we could do real analysis after this, that would be fine.
Sure.
It's one that I could go over 10 times and still
You like it?
get value going over it again. Not just like it, get value from doing it. Like right now, doing discrete math is kind of a waste of my time. I'm not really getting anything from it anymore. But real analysis, That's one that you can keep doing and keep getting value out of.
I'm excited for any of those.
Alright, anyways, we have a quick corollary from this one. What's our corollary? We're going to use beta now. Beta is equal to the set of all infinite binary strings. So a binary string, 1, 0, 1, 1, 0, 1, 1, blah, 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 that goes on forever. An infinite binary string. So we're going to show that beta equal to the set of all infinite binary strings is uncountable. With me?
So it's
Notice that these were kind of like infinite decimal strings. So now we're kind of just switching to infinite binary strings. Same exact type of proof. So assume by way of contradiction that beta is countable. What does it mean for it to be countable? That would mean that there exists some function from the natural numbers to beta such that that function is a bijection. Or more importantly, that function's on 2. We're going to show that it's not on 2. Alright. We're going to construct x in beta such that x's nth bit is 0 if f of n is 1, otherwise it's going to be 1. So x is going to be equal to, let's see, this one's first bit is 1, so we're going to put 0. This one's second bit is a 1, so we're going to put 0. This one's third bit is a 1, so we're going to put 0. This one's fourth bit is a 0, so we're going to put 1. And we're going to continue on constructing x that way. X is going to be different from 0 because they differ in the first bit. X is going to be different than 1 because they differ in the second bit. X is going to be different from 2 because they differ in the third bit, etc. So that's how we're constructing x. Then, for all n in the natural numbers, f of n is never equal to x, since they differ in the nth bit. Therefore, x is not in the image of this function. Therefore, this function is not on 2. Contradiction. Therefore, beta is uncountable. So, there's another uncountable set.
Why can't you do that with natural numbers?
Why can't I show that the natural numbers are uncountable? Because I can show that they're countable. I can map 0 to 0, 1 to 1, 2 to 2.
Maybe you could like do that exact same thing.
You can't do that exact same thing.
What's stopping it?
What's stopping it?
Take your table and just put in only natural numbers.
Because it
Why
will
couldn't
be
you
that
keep
eventually.
them sideways?
Because a natural number doesn't have an infinite expansion.
Okay, yeah, okay.
Okay. So it's this property that these things that we're talking about have this infinite expansion that seems to be giving us a problem.
I see that, okay.
And so the rational numbers, the thing about the rational numbers is they could always be expressed in a way that they have a finite expression.
So infinity ends.
Infinity ends?
Take an infinite number from natural numbers. Where does that not exist?
Well, ultimately, what we're showing here is that there's different notions of infinity. What is the size of the natural numbers? It's infinite. What's the size of the reals? It's infinite. Yet the size of the reals is a different infinite than the size of the naturals.
That's fair, okay.
So even to say infinite, what infinite are you talking about? Okay. So let's make a note here. Note, a Turing machine M has an exact definition. It's equal to Q, sigma, tau, not tau. What is that? Gamma. Q, sigma, gamma, delta, Q naught, Q accept, Q reject. That's the exact definition of a Turing machine. Where what? Q is a finite set of states. Sigma here is a finite alphabet. It's an alphabet. Alphabets by definition are finite. Gamma here is also an alphabet. Delta here is mapping combinations of these things with combinations of these things. But still a finite number. So the point is finite, 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 finite. Any definition of a Turing machine is finite. That makes sense? There's no such thing as an infinite definition for one Turing machine. Every Turing machine's definition is finite. So a Turing machine M is composed of finite sets, and so it's finite. Thus the set of all Turing machines M, the set of all encodings of a Turing machine, convert to strings, M, is a countable set. There's a countable number of possible Turing machines in existence. There's a countable number of possible programs you could write. For those of you comfortable with programming, you know that every program ultimately goes down, gets composed to a binary of zeros and ones. If I just wrote out all the possible strings of zeros and ones, I would have eventually written every possible program. If I start writing just 0, then I write 1, then I write 0, 0, then 0, 1, then 1, 0, then 1, 1, and I kept writing that forever, I would eventually write every possible program.
True.
Right? Yeah. So the set of all possible Turing machines is a countable set. We eventually enumerate every single one of them. Does that make intuitive sense?
The set Turing machines?
The set of all possible Turing machines
Okay.
is a countable set. You could list them all. There's an infinite number,
That makes
but you
sense.
could list them all.
That's one part that was confusing. I thought that you were saying it wasn't infinite by saying it's finite.
Every Turing machine is finite. It can be arbitrarily large, but it's finite.
Okay.
Just like every natural number can be arbitrarily large, but it's still a finite number.
Does finite mean not infinite?
Yes.
Okay.
So why did you show strings and proving that Turing machines are forever? Where there's infinite amount, the set of Turing machines is countable.
The set of possible Turing machines is countable. I don't understand your question.
You wrote strings down there, and I'm wondering where that came from.
I wrote strings. Oh, these things?
Yeah.
Okay. So when you type a program and it gets compiled so that the computer can read it, it's ultimately just a big file of zeros and ones because all computers read binary.
Yeah.
So if I start writing out just like this, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, and I kept going forever, I would eventually write out every possible program in existence.
Okay.
A program and a Turing machine are logically equivalent.
Oh, okay.
That's probably the piece you're missing. When you run a program on a computer, that's simulating a Turing machine on a Turing machine.
Okay. Yeah.
So that's intuitively how we think about Turing machines as programs.
I was also a little confused because I was thinking you were referring to the, I don't know how the term, but like the logic rather than the string that you inject.
Not sure what you mean.
Shoot. Okay, so you have the logic, right? You have the bubbles, and if this, then set this, and then you're reading your string, right? So you have your language,
Okay?
or your string, and then you have your Turing machine.
Right.
And I was thinking you were talking about like every possible logical combination of the Turing machine, and not. Oh wait, I got it now. You're taking the logic and converting it into the string, which is
Right.
okay.
Take your program, now compile it
Yeah.
to binary.
Yeah, that makes sense now. Okay.
There's one possible encoding of a Turing machine. There's a bunch of encodings of Turing machines, but pick one. Then whatever that encoding is, you can use your encoding to list out every possible Turing machine.
We never actually talked about converting. I don't know if it's even relevant, but converting a Turing machine into ones and zeros.
No, but we talked about how you could convert it to a string. We started with a graph, showed how you could create an encoding of a graph. Lightly talked about how you could do it with the Turing machine and moved on our way. How you do it isn't particularly relevant.
All right.
It's just that you can do it, and binary strings is one way to do it. It's just that this might be comfortable for programmers, but for someone like him, it's going to feel out of the blue. Whereas the way we did with graphs is probably going to feel like a more natural way.
Yeah. Well, I don't think that's understandable by anybody.
It is.
I mean, you get enough of it, it's overwhelming.
Well, you write, I guess you didn't do the CS degree, but one of the things you do with the CS degree is you build a compiler.
Yeah.
And so you actually go from the process, you specifically take the things that you type. So I wrote a compiler for C++. It couldn't do all of C++, just a very limited part of it. And I convert it from that to the basic instructions that you give your computer. And then each of those basic instructions have an encoding to bytes.
Right.
And so I actually wrote it out. And so I could compile some little hello world program to the bytes. I don't think I had a print statement in there, so I couldn't do hello world, but I could do one that simple calculator that doesn't print out any answers, but it will calculate it and store your answer somewhere.
I definitely need to do that to understand
Yeah.
Multi level.
But, yeah, so it is understandable. You just gotta go through the pains of doing it. Memorizing which ASCII goes to which byte is annoying, but. Anyways, doesn't matter. Point is that came time. Okay. So, now let's prove something absolutely crazy. This, I think, is the coolest thing we're proving today, but maybe you'll think otherwise. We're going to prove that some languages are not even recognizable. What's the difference between decidable and recognizable? A decidable language is a language that a Turing machine can say, for every string in the language, a Turing machine can say, yes, that string belongs in the language. And for every string not in the language, a Turing machine can say, no, that string doesn't belong in the language. That's decidable. Recognizable would be the Turing machine isn't guaranteed to say a string doesn't belong, but if you give it a string that does belong, it will be able to say, yes, this string does belong. Make sense the difference? No? We go back to, you remember talking about Diagonalization equations? Something that looked like 6x squared plus 13y minus 6z equal to 0. And you're looking for integers, x, y, and z, that you can plug in that make that statement true. Now, it turns out, we didn't prove it, but it turns out, you just have to kind of take my word for it, that there is no algorithm to find the integers that match that. But, if I were to give you integers that did work in this, then you could check it and say, yes, it works.
So the ones that do work are recognizable?
So the ones that do work are recognizable. So the set of Diagonalization solutions are recognizable.
Not decidable.
So you're saying...
Sorry, I'm saying that wrong.
Oh.
If I give you a Diagonalization equation that does have solutions, I'm not telling you what the solutions are. I tell you that this one does have solutions.
Okay.
You can eventually find those solutions
Okay.
by trying every combination of integer. You can try 0, 0, 0. Then you can try 0, 0, 1. Then you can try 0, 0, negative 1. Then 0, 1, 0. 0, negative 1, 0, etc. And you can try every possible combination, slowly building up higher and higher. Eventually, you'll try the combination that works. Now what if there was no combination that worked? Would you ever figure that out? No. Because even if you tried all the way up to 10 trillion, maybe the thing that works is 10 trillion and 1. You never get a stop.
Can we figure out if it's recognizable or not?
So it's recognizable means that if you give me Diagonalization equations that have solutions, I can eventually say, yes, here's a solution.
To it, you can find solutions, but can you figure out...
But if you gave me one that didn't have solutions, there's no way for me to know it doesn't have solutions. Because I just have to brute force keep trying.
Okay, so the only way to figure out if it is recognizable is to find the actual thing that fits.
So recognizable means that you could eventually say yes.
Yeah.
Decidable means that you could eventually say yes, or eventually say no.
Yeah. Yeah.
So, set of Diagonalization equations that have an integral root that have a solution to make it equal 0, that's a recognizable language. If I give you one that for sure has a solution, you can eventually find the solution. But if I give you one that didn't have a solution, there'd be no way for you to know. You might be able to know with a particular one by thinking about it, but there's no general formula you could write that would always spit out the correct answer. Okay, so that's an example of something that's recognizable, but not decidable. So we're going to prove that some languages aren't even recognizable. You could not even build an algorithm to say yes for everything that belongs in the language. Alright, that's what we're proving. Okay, so some languages are, that's an E, not C, are not recognizable. Let our alphabet be 0, 1. And before we get into L, let's really quick remind ourselves, what is sigma star? So if sigma is 0, 1, what is sigma star?
All possible binary strings?
All possible binary strings. You pick something from here, compose with something from here, compose with something from here, as many times as you want, including the empty string. So this is a set, sigma star is a set of all possible binary strings. So L is a set of all A's, where A's is a subset of the set of all possible binary strings. Or in other words, L is a set of all possible binary languages. If your language is a binary language, then it's going to only have binary strings in it. So it's going to be a subset of the set of all possible binary strings. Okay? So L here is a set of all possible binary languages. A binary language, here's a simple one that we've used a bunch of times, 0 to the n, 1 to the n. There's a binary language. That's going to be one of the things in L. Another way to think about it is L is equal to the power set of the set of all possible binary strings. It's equal to the set of all possible subsets of the set of all binary strings. I don't know. Whichever of those are doing it better for you, or just writing it out in words, L is the set of all binary languages. Any possible binary language you can come up with, it's in this set. Because then it would be a subset of the set of all binary strings.
Why are you saying language, not strings? When did it turn to language?
Sorry. A set of strings is a language.
Oh.
So sigma star is a language. It's a language that contains every possible binary string. A contains only some of those binary strings. A is still a language. So A is a language of binary strings. L is a set of all the A's. It's a set of all the languages of binary strings. It's a set of every possible subset of the language containing every binary string. I don't know. Say it until it clicks. We good?
It makes sense to me.
Okay. So that's what L is. Now, since there are a countable number of Turing machines, and each Turing machine can only recognize one language, it remains to show that L is uncountable. There's a countable number of Turing machines. Each Turing machine can only recognize one language. If I can show that there's more languages than there are Turing machines, then there has to be languages that can't be recognized by a Turing machine.
So it's kind of like that problem with the...
Exact same thinking.
Okay.
Well, we'll come at it a little bit different, but very similar thinking.
Okay.
So we're going to show that the set of all possible languages is uncountable. We know that the set of all possible Turing machines is countable. If we can show that the set of all possible languages is not countable, then there has to be a language that can't be generated by a Turing machine, that can't be recognized by a Turing machine. That make sense? Big picture what we're doing?
Yeah.
Okay. Now, how are we going to show this? To show that L is uncountable, we will show that L has the same size as beta, the same beta we were talking about over here. Over here, we already proved that beta was uncountable. If I can show that L has the same size as beta, then L has to also be uncountable. Make sense? Okay, so we will show that the size of L is the same as the size of beta, and so it's uncountable. That's where we're going from here. Now, first thing to know is to observe that all the strings in sigma star can be ordered in some ordering. S0, S1, S2, dot, 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 dot. We can order all the binary strings in some ordering. In other words, the list of all binary strings is a countable set. We can order it somehow. With me? And so, sigma star, we can rewrite it as S0, S1, S2, dot, 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 and we can label all the strings in there this way. Now, we're going to jump and do an example in the middle of our proof, and then get back to the proof to help you understand exactly what we're saying. And big picture what we're going to do in the proof. So, sigma star, I can say, is the empty string, then 0, then 1, then 0, 0, then 0, 1, then 1, 0, then 1, 1, then 0, 0, 0, etc. And we can eventually list out every possible binary string following that pattern. You with me? Now, what I'm going to do is for any language you pick now, you pick any random language A. That's a language in binary strings. The A I happen to choose here is A is equal to 0 to the n, 1 to the n, union with 1 to the n, 0 to the n. That's the A I happen to choose here. But pick any A you want. A is coming out of the set L. One of these A's. All I require is that A is a subset of the set of all binary strings, or in other words, A is a language of binary strings. Doesn't matter which one you pick, but just pick one. I happen to choose this one. Completely arbitrary for the example. Pick any A you want. Now, if this string, remember, A is a subset of this. So for each string here, we just need to answer the question, yes or no, does it belong in A? If the string belongs in A, I put a 1 for B here. If the string doesn't belong in A, I'm going to put a 0 for B. You with me? So looking at it, if this is my language A, do we put the empty string in there? Yes.
Yes.
So we put the empty string in there. Do we put 0 by itself in there? No. So we have a 0 here, and we don't put it in. Do we put 1 by itself in there? No. So we have a 0 here, we don't put it in. Do we put 0, 0 in there? No. So we put 0 there, don't put it in. Do we put 0, 1 in there? Yes. So we put a 1 there, we put 0, 1 in the set. Do we put 1, 0 in there? Yes. So we put a 1 there and put it in the set. And we'd eventually include a string like 0, 0, 0, 1, 1, 1.
So I'm not.
And A goes on, and A is also infinite.
How did we get 0, 1 from that A over there again?
A is some number of zeros followed by the same number of ones, or some number of ones followed by the same number of zeros.
It's union, doesn't it combine them?
It's this or this is union.
Oh, yeah.
So one or the other.
Okay.
But the point to note is A is some subset of this, right? And so for each language A, we can create a corresponding infinite binary string, where the binary string is 1 in the first place if we included the first string from sigma star.
Okay.
It'd be 1 in the second place if we included the second string. Oh, we didn't include the second string, so we put 0 in the second place. I'm trying to create a one-to-one mapping between our languages and infinite binary streams. And this is what my mapping is going to do. We're going to map binary strings, every infinite binary string, to a corresponding language. So here's your infinite binary string. It corresponds to this language. And notice that every single language is going to have a corresponding binary string. We call this the character sequence of the language A. Just terminology. You with me? So that's going to be my function. Because remember what I'm trying to do. I am trying to show that the size of L and the size of beta are the same thing. How do I show that they have the same size? I need to create a bijection between the two. I need to come up with some function that maps beta to my language, that maps beta to L, that's both 1 to 1 and on 2. How am I going to do that? I'm going to say for any binary string you have like this, map it to this language. And here's how you get the language from the corresponding binary string. You see how any binary string you pick here, infinite binary string, will give you a corresponding language? And every binary string is going to give you one and only one language, and every language is going to have a corresponding binary string. Every language is eventually going to get mapped, so it's going to be a bijection. Therefore, these two sets are the same size, because we create a bijection between the two sets.
Where did you put beta? I'm not seeing beta ever.
Let f be a function from beta to L. What is beta? It's a set of all infinite binary strings.
Oh yeah, we need to find that.
So here's an example of something in beta. This B right here is in beta. And this A right here is in L. And I'm showing that everything in beta maps to something in L. And it maps to one and only one thing in L.
Can you do that? Isn't that backwards?
Yeah, I wrote it backwards because this is in that.
Yeah, okay.
So, just trying to help you read it, making up notation. But I think you get it, right?
Yeah.
Okay. So here's our function. Let f from beta to L such that f of b is equal to a. Remember, b there comes from beta, so b is an infinite binary string. So f of b equals a, where the ith string is in a if and only if b's ith bit is a 1. So if b's ith bit is a 1, then the ith string ends up in a. If it's a 0, that string does not.
Why aren't we using n? I just messed it through.
Because n we usually use for the whole count at the end, I is for an arbitrary place in there. Make sense? So, that's how we map b to a. If the ith bit of b, is a 1, then we include the ith string of sigma star.
Yeah.
If the ith bit of b is not a 1, then we do not include the ith bit of sigma star, or the ith string of sigma star, sorry. I think you understand what I'm saying, I just keep using the wrong language.
Yeah, I get it.
So let f be a function from beta to L such that f of b is equal to a, where s sub I, we talked about s right here. The ith thing, or right here, the ith thing in here is in a if and only if b's ith bit is a 1. And we call b a's characteristic sequence. So b is the characteristic sequence of a. It's the infinite binary string that corresponds to language A. So then if a and b, so now these are both infinite binary strings, if a and b are infinite binary strings such that they give us the same language, then they must have the same, if they have the same language, they must have the same strings in them. And if they have the same strings, then they must have the same bits. And therefore, they must be the same. Therefore, A and B must be the same, and so it's 1 to 1. Same language means same strings, means same bits, means...
Where'd you get little a from?
So we start out with a random little a and little b from beta,
Oh,
such that they have the same language.
okay.
So if A and B give us the same language, then that means that their language has the same strings.
So now A.
If the language has the same strings, then they have the same ones in the same places.
Yeah.
If A and B have the same ones in the same places, then A and B are equal.
Yeah.
Or, in other words, F is 1 to 1. If the outputs are equal, the inputs are equal. If you have the same languages, you have the same characteristic sequences. Does that make sense?
They're both from B though. They're both from beta. A and B are from beta, not
Sorry, little a.
little a is from beta and little b is from beta.
Little a is an infinite binary string.
From beta, yeah.
Yes, from beta. Little b is an infinite binary string.
So
F of a is now a language. What does F do? It maps infinite binary strings to languages. Doing this.
okay, so F of B is a language. And F of A is a language.
F of a is a language, F of b is a language.
The languages have the same strings.
So since F of A and F of B are the same languages, then they must have the same strings.
Yeah.
If they have the same strings, then they must have the same characteristic sequence.
Good.
But A and B are the characteristic sequences. So A and B must be equal.
Yeah.
So F's 1 to 1.
Okay.
Good?
That makes sense. That part.
Now, let A be anything in L, be any language. And observe that it must have some characteristic sequence. Call it B. B is going to be an infinite binary string, so it's going to be a beta, so F of B equals A, so every language eventually gets mapped to. Right? Okay? Therefore, A is in the image of F. It was a language that eventually got mapped to, therefore F is on 2. Since we showed this 1 to 1 and we showed it's on 2, then F is a bijection. Therefore, beta and L are the same size, therefore L is uncountable. Which is what we were after. So all that was a bunch of work to show that the set of all binary languages is an uncountable set. There's a countable number of Turing machines. There's an uncountable number of languages. Therefore, not every language has a corresponding Turing machine that goes to it. Only some languages do. The languages that aren't recognized by any Turing machine are by definition unrecognizable languages. They can't be recognized by any Turing machine.
Could you give us an example of an unrecognizable language?
Can I give you an example of an unrecognizable language? Yes, but it will not appeal to your intuition anyway. The acceptance problem of Turing machines complement.
Oh, he's talking about as well back.
So that is a set that's not even recognizable. We'll prove it, but when we prove it, it's not going to be a very satisfying proof. And you'll still have no intuition as to why it is. We'll just show you that it is.
I feel that way about this one. You're just saying this is it, and I trust you. I just.
Well, this one's better because you know that there's an uncountable number of infinite binary streams. Right? That's what we proved over here. Are you comfortable with that? The number of infinite binary streams is like the number of real numbers.
Okay.
You good with that?
Yeah.
So whatever it is, it's way bigger than the set of natural numbers. It's uncountable.
Okay.
Now I showed you that I can pair off between every infinite binary string. I can find one and only one language that matches to it. If you pick this binary string, here's the language that matches to it.
Okay.
I just barely thought we were proving that languages are not recognizable, and then we just at the end said that beta is the same as L.
Yes, because beta is unrecognizable, or beta is uncountable. So L is uncountable.
Oh.
So let's follow through the logic one more time. Over here, we showed beta. First off, we showed R is uncountable.
Yeah.
How big is the real numbers? It's uncountably big.
Yeah.
Then we said beta is also uncountably big. Then we said, look, I can create a pairing between everything in beta and all the possible binary languages. I can do a one-to-one pairing. For every infinite binary string you choose, I can give you one and only one language that corresponds to it. So then the set of all languages must also be uncountable.
I'm seeing this now.
Okay, the number of Turing machines, countable. That's like the natural numbers.
Yeah.
Turing machines is like natural numbers. Languages is like real numbers. So you can't map all the Turing machines to the languages. That would be like mapping all the natural numbers to the real numbers. And you can't do that. Therefore, there has to be languages that we can't map to. Or in other words, there's unrecognizable languages.
Okay, I get that there's unrecognizable languages. How you're proving that there's unrecognizable languages, is it similar to the strategy you use here by grabbing one of every...
No. So here I was showing that however big the real numbers are, they're bigger than the natural numbers.
And it's the same with this. For all, however big the computation...
No, we're doing it a little bit different.
Okay.
But you're good with here what we were showing.
Yes.
Here we're showing the size of the real numbers is bigger than the size of the natural numbers.
Yeah, I got all of that.
Here we showed that the size of beta is the same as the size of the real numbers.
Now...
Roughly.
When you have, for instance, you have your n, and you have 0, 1, 2, 3.
Uh-huh.
Is that the Turing language, or like the...
This right here, I'm just listing out the natural numbers.
Okay, so you're listing all the natural numbers
Yes.
for your rows there.
I'm showing that the table that we have right here, it can't exist.
Okay, but like, why is it the number 0 is 1, 0, 1, 1, 0, 1? Like,
Completely arbitrary.
completely arbitrary. Okay.
But if you were to create some function, let's go back up to this one. We assume that you created some function that mapped all the natural numbers to one and only one thing between 0 and 1. We pretend that you have one. I'm going to show you it's impossible that you have one. So I say it's impossible to come up with a function like this. Chandler stays up all night, and he comes back to me and says, nope, I found one. And I say, let's test that. Here's what I want you to do. Write out whatever the number is that 0 goes to. Whatever it is, doesn't matter. Write out whatever 1 goes to, 2 goes to, 3 goes to, 4 goes to, 5 goes to, 6 goes to, etc. Now I want you to write out this new number x. And I want you to write it so that its first decimal is 1 more than this one's first decimal. Its second decimal is 1 more than this one's second decimal, unless the second decimal is a 9, then we just do an 8. Its third decimal is 1 more than this one's third decimal. Its fourth decimal is 1 more than this one's fourth decimal, etc.
And I get that. I get all that.
So here's going to be a number that you miss every time.
Yeah, absolutely. It makes sense because every one of all these have 1 digit that's off.
So this table that he came to me and he says, here's the mapping, doesn't work. It's false. You can't create this table.
Right.
Okay, so that was showing that there's more real numbers than there are natural numbers.
Yes.
Now, we barely showed there's the same number of languages as there are real numbers. Here's roughly what we said. We said the size of all Turing machines is equal to the size of the naturals.
It's almost like saying for every Turing machine, there's an infinite amount of language.
Now, well, kind of.
Okay.
So we said the size of the Turing machines is basically the size of the naturals.
Uh-huh.
And we said that the size of all languages is basically the size of the reals. Since you can't do a one-to-one mapping from here to here, since that's impossible, then you can't do a one-to-one mapping from here to here. So there's more languages than there are Turing machines. And the way you said it shows you have good intuition. There's infinite number of languages for every one Turing machine. Kind of a weird way to say it, but yes.
It kind of makes sense. I'm just wondering how you're proving it.
Here's what we proved. Let's write it all out. We roughly said that the number of Turing machines is equal to the number of natural numbers is less than the number of reals is equal to the number of languages. That's roughly what we proved.
Yes.
So, this is bigger than this.
And you said that you came about it in a way, and it's using a different strategy other than the one that you're using here. For instance, the strategy we use here is we change the digit of.
So this proof right here is showing this part. It's showing this part. It's showing n is smaller than r.
Yeah.
This right here is showing this part. R is equal to L. Use different strategies there. To show this, you show that you cannot map this to this. To show this, you show that you can map this to this.
Okay, so this is all just to prove that languages are basically like all the rational numbers.
Well, I don't know what's all to prove, but one of the things it proves that's very useful is that the number of languages is more than the number of Turing machines. And that's a useful thing to know.
So as long as the number of languages is equal to the number of rationals, then it will always
Reals.
reals. Yeah. It's equal to the number of reals, then it will always be greater than the number of Turing machines.
Right. And when we think about languages, intuitively we think about languages as problems or solutions to problems. That means that there's problems, that there's no such thing as an algorithm to solve that problem.
Well, say that all over again.
We think about a language as a problem,
Yep.
or as a solution to a problem, however you want to think about it.
Okay.
Like we call the acceptance thing over there, we call it the acceptance problem. For any problem you give me, I can give you a corresponding language. They're the same thing. Language is a computer scientist way, or a computation theorist way of talking about a problem. So when I say that there are languages that cannot be recognized by a Turing machine, that's equivalent to saying that there's problems that you cannot come up with an algorithm to solve. An algorithm, same as a Turing machine. A problem, same as a language. There's unsolvable problems out there.
And that's your
That a Turing machine, there's no such thing as an algorithm to come up with a solution to that problem.
And that's A, right? A is the language that cannot be mapped on a Turing machine. The A that you gave.
No, a Turing machine can do that, if that's what you're saying. Very
It's
easily.
not a Turing machine that can solve not Turing machine can solve all problems.
There's no such thing as an algorithm to solve the problem.
And algorithms are Turing machines.
Algorithms and Turing machines, same thing.
Yeah.
By definition, an algorithm is what a Turing machine can do.
There's no algorithm to solve.
There's problems that you cannot come up with an algorithm to solve.
It's so weird.
To even come
I
up with
feel like
solutions.
if you create the problem, I can come up with a Turing machine to solve it.
Okay. I want you to come up with a program that tells me when a Diophantine equation does not have any solutions.
I don't know. I have to understand what you mean by that.
A Diophantine equation is something like 6x squared plus 7y plus 8z to the 4. It can be anything like that. Your algorithm has to come up with, it has to answer the question, is it possible for me to plug in integers x, y, and z that ultimately make this whole thing equal to 0? And I'm going to give you any Diophantine equation I want. Your program has to answer that there are integers I can plug in for x, y, and z that make this equal to 0, or there are not. It has to answer yes or no.
And I could try every single integer there is.
No. Let's say, for example, that this has no solutions. You can never make this equal to 0. How would your algorithm ever figure that out? Because you can't try every possible integer.
Why not?
Because then your program runs forever. And that's what we mean by your program never halts. There's no difference between maybe you haven't let it run long enough to get the answer, and there is no answer. There's no way for your program to know the difference.
Oh, that's true.
Do I just need to run longer, or is this a waste of my time? There's no way to know.
Yeah, makes sense. And that makes it.
Now this problem is still
Undecidable.
recognizable, it's just
Undecidable.
not decidable. And now we saw that there's languages that aren't even recognizable. That if I promise I'll only give you things that actually had the solutions, you still couldn't say yes every time. And the only example we have of that so far is the complement of the acceptance problem. Anyways, so yeah.
Okay, so all of the language that's not in it's not what's the word?
Recognizable?
No, come on. Bijection.
Okay,
So
bijection.
any language that does not have bijection is unrecognizable. Or no, sorry, it's undecidable.
No. So a language is Turing recognizable if you can create a Turing machine to recognize that language.
And it'd be a bijection. All Turing machine all languages have a bijection with all recognizable
Yes.
languages.
So if I created the list of all possible recognizable languages,
Uh-huh.
and I created the list of all possible Turing machines with no duplicate Turing
It'd be a
machines,
bijection.
duplicate meaning two Turing machines that generate the same language,
Oh, okay.
then yes, we could create a bijection between those two things.
Cool.
Because every Turing machine generates one and only one language.
Uh-huh.
And if two Turing machines, if we mean by different Turing machines means they don't generate the same language, then it would be a bijection because you want to have two different Turing machines generating the same language.
So it's the fact that we have unrecognizable languages indicates is why they're not the same size, and they're not bijection, and that is okay, yeah, and so all right, yeah.
No, it has very strange theoretical consequences that are not intuitive at all, and it's one of those things that it's a little bit surprising every
Well,
time
it
you
makes
think
a lot
about
of
it.
sense now that you get it. I mean, when it clicks.
All right. So, now we've shown that there are uncountable languages, that there are unrecognizable languages, because the set of all languages is uncountable. The set of Turing machines is countable. So there has to be languages that you can't map a Turing machine to. Make sense? Okay. Now, what we have just barely shown is that while a set like sigma star is countable, its power set is uncountable. Remember, L was its power set. Now, I guess this is more just for Anna than you guys, but one of the things we talked about a lot in other classes like real analysis and discrete math is that while the naturals aren't the same size as the reals, if you take its power set, now it is the same size as the reals. And it's a similar type of thinking that shows that. Just because I've never been able to show you an argument like that before. How you have a countable set, but if you take its power set, suddenly now you've got something uncountable. And this is showing that. Which I think is awesome. That's why I like this proof so much. It's very amazing that you have a countable set, take its power set, and now it's uncountable. Because the cross product of two uncountable sets is still just uncountable. The cross product of 100 uncountable sets is still uncountable. Or is still just countable. But then you take the power set and something that somehow that's something even more powerful. Very interesting operation. Take the power set. Alright, so now let's finally get to what we promised we'd do at the start of class. Prove that the acceptance problem for Turing machines is undecidable. Finally gonna prove this. First time we've proven anything is actually undecidable in this class. Till now you kind of just been taking my word for it. So let's prove that this is actually undecidable. What's the acceptance problem for Turing machines? It's the set of all Turing machines encoded together with a string that that Turing machine accepts. Right? Write it out really quick. It's going to be equal to the encoding of MW.
Where M is a Turing machine.
Yeah, where M is Turing machine.
Accepting W.
Yeah.
The 18 is undecidable.
Accepting W. That's what the acceptance problem is. So every possible Turing machine and every possible string W, that Turing machine accepts W. So if this Turing machine accepts an infinite number of W's, this Turing machine is going to show up here an infinite number of times, one for each W it accepts.
So can we go back real quick?
Sure.
I wasn't there when you introduced Turing machines, or maybe I was, but I forgot. But what's the difference between a Turing machine and DFA? Unless it's too long.
Random access memory. So in short, a DFA, if we draw out a DFA, so go back to just a simple one I've drawn over there. We have its states. We'll call this state 1. We'll call this state 2. We said it goes over here on a 1, comes back on a 1. This was an accept state. And on a 0, it just slips to itself. So here's a DFA.
Yeah.
Now we only wrote the state control. Really, a DFA is like this, and it has a pointer. That's just a state control, and it has a pointer to some tape with the input string on it that's reading. 0, 1, 1, 0, 1, 0. And so it runs through this input string, simulating this. If when it's done reading the input string it's in an accept state, it accepts. If when it's done reading the input string it's not in an accept state, it rejects.
Yeah.
The Turing machine has a similar thing. It has a state control similar to this. But unlike with the DFA, every time it reads a symbol, it has to go to the next symbol and just read that. And then it has to go to the next symbol and just read that. Okay. A Turing machine can go left and right reading these symbols willy-nilly, and it can change the symbols to whatever it wants.
Okay.
Okay?
So you don't really need to strain into a Turing machine, you could just create its own.
So it's like it has access to all this memory where it can write stuff down, keep track of stuff. Like when you do some long operation of multiplication, you write things down that you keep track of and slowly come up with your answer. Now your Turing machine can do the same thing.
Okay.
And it has, this tape is infinite, by the way, with the Turing machine. It goes on forever. So you have access to an infinite amount of memory. So you can potentially write anything down you want. So that's high level the difference between the two. But you're far better off to watch the lecture.
Yeah, probably.
Okay. Acceptance problems for Turing machines. So we're going to prove that the acceptance problem is undecidable. Assume, by way of contradiction, that the acceptance problems for Turing machines is decidable. What does it mean for a language to be decidable?
You can decide yes or no.
Some Turing machine decides it. Some Turing machine can always say yes when it's in there and no when it's not in there. So if we're going to assume that this is decidable, that means that there must exist some Turing machine H that decides it. That's what it means for a language to be decidable. There's a Turing machine that decides it. So if this language were decidable, there would have to be some Turing machine we're going to call H that decides that language. In other words, whatever H is, if I give it a Turing machine M and a string W, if I feed that into it, and M accepts W, then my Turing machine H will say yes. And if it turns out M does not accept W, my Turing machine H will say no. No such thing as Turing machine H. Can't exist. We're assuming by way of contradiction that does exist. And we're going to show that leads to an impossible worldview. Okay. So now we're going to construct a new Turing machine, call it D. D, on input M, so you feed it an encoding of a Turing machine, what is it going to do? It is going to run on H, M, and the string version of M. So remember what H takes. H takes any Turing machine and a corresponding string. D is going to plug into H, the Turing machine M, and the string version of M. Whatever you get when you convert M to a string. Think about every Turing machine can be converted to a binary, right?
It can be broken.
Think about a Turing machine as a piece of software you run on your computer. It can be converted to a binary file that the computer runs, which is just a bunch of zeros and ones. So it's going to give it, so D is going to give H, the Turing machine M, and all those bunch of zeros and ones. Maybe M accepts all those strings, maybe it doesn't. Most likely M probably doesn't accept the string version of itself, right?
Okay.
But maybe by some freak coincidence that works, and it happens to accept it. Who knows? So weird, right? So we're going to run H on M and the string version of M. Now notice what happens. If H accepts, then our machine D is going to reject. If H says, yes, when you run this on here, it works, then our machine D is going to reject.
Okay.
If H rejects, our machine D is going to accept. So it's just doing the opposite of whatever H does. You with me?
Yeah.
Okay,
Yeah.
so know something. Then D accepts some machine M, if and only if M does not accept itself. When does our machine D accept? D accepts, sorry, up here. D accepts when H rejects.
And D.
And what does H do? H runs a Turing machine on itself. Right? So our machine D accepts M if and only if M does not accept itself.
Yeah.
Now we can plug D into D. So then D accepts itself if and only if D does not accept itself. Contradiction.
Yeah, I see that.
Therefore, no such D can exist, which means no such H can exist. Because if you could build H, you could definitely build D. But D is impossible, so H is impossible.
I'm trying to imagine how this would actually work in practice. Like, let's say some language everyone understands, like JavaScript. You're using you take you have JavaScript and you take a input of JavaScript and run it like an eval on it. Evaluate this code, or
Here's one way to think about it. Harley created some server, and he says, on my server, you can send it a program and a string to run, and my server will say, yes, that string runs on the program, or no, my server does not say, or my server says, no, that string will not run on that program. So I hook up to your server called H, and now I may create D. And what am I going to do with D? For any machine I'm given, for any program I'm given, I'm going to send you that program to Parley, and then I'm going to take that program and convert it to just this binary file. And I'm going to send you that string. And you're going to tell me yes or no, that string is accepted by that program. You can run this string on this program and we're fine. Yes, or you can't run this string on this program. We're not fine. Your magical server is able to do this.
And the strings are identical.
No. This is the program I send you. And this is a string encoding of that program.
Okay, but it's exactly the same as if
You could convert this to this.
Okay, I just
It's the
wanna-
same way. Here's a simple way to think about it. There's a difference between a JSON string and an object, but I can convert every object to JSON string.
Mhm.
Here's a JSON string, here's the object.
Yeah. Okay, good.
Same thing. So it's not a JSON string and an object, those are different things, but you can convert any object to a JSON string.
Okay.
So this is the actual data of my program I send you. This is an actual string of zeros and ones. Like stored in an actual string object. Okay? So that's why I send it to you on the server. Your magic server is able to run this on this and tell me if it works, yes or no.
Like it has the right syntax or something.
Yeah, crashes, yes or no. We can make this a crashes, yes or no.
Okay.
We'll say doesn't crash is the same as accepting, crashes is the same as rejecting.
Uh-huh.
So you're going to say this is going to crash, yes or no. Now I say, here's what my little program is going to do. I'm going to send this to Parley. If Parley says, yes, it's going to work, this string can run on this program, I'm going to say, reject. If Parley says, no, this string can't run on this program, I'm going to say, accept.
Okay.
So now someone comes along, and they feed my program into myself now. So they give me the binary for my own program, the data. So now my program takes as its input D here. And I send that to Parley. I say, Parley, hey, when I run myself on me, am I going to accept? If you say yes, I'm going to accept, I'm going to reject. If you say yes, I'm going to reject, I'm going to accept. I'm going to intentionally do the opposite of what you say I'm going to do. So therefore, you can't predict what I'm going to do. Because I'm intentionally doing the opposite.
I can't predict that you're doing the opposite.
You can't predict what I'm going to do. Because if you say I'm going to accept, then I'm going to reject. Right? Just to spite you.
Was I predicting that you were going to also accept?
Yes. You're telling me what am I going to do.
Okay.
You're saying, when you run my program D on myself, here's what you're going to do. If you say that I'm going to accept, I'm just going to reject. If you say that I'm going to reject, I'm just going to accept.
Okay.
It's kind of like you're trying to predict the future. I say, Parley, in 5 seconds, am I going to pick up that chalk, yes or no?
I say yes.
Yes.
and
If you say yes, I don't do it. If you say no, I say you're wrong again. You can't win.
Right.
It's the same thing here.
Okay.
Okay, so that's one way to view it. We can also view this with the sort of diagonalization method here. We could list out, erase that. We can list out, since Turing machines are countable, we can list out all the possible Turing machines. We can say, here's M1. Maybe try and write it a little bit better. Here's M1. Here's M2. Here's M3. Here's M4. And eventually, we would list out my Turing machine P. You with me? And here is going to be all the encodings of the Turing machine. Here's the encoding of M1. Here's the encoding of M2. Here's the encoding of M3. Oh, we did M4. Here's the encoding of M4. Dot, dot, dot. And eventually we'll list out the encoding of D. My program up there. Dot, dot, dot goes on forever. Dot, dot, dot goes on forever. Now this table, we're just going to say whether H says we accept or reject. So H is a program. You give it a machine and an input. So we can write down everything that H will ever say here. Fill it out as a table, kind of like the way we fill out the rationals. You with me? Now it doesn't matter, we just make up stuff. I'll use A for accept, R for reject. Now M1, when we run it on this encoding, what does it do? I don't know, we'll say it rejects. And let's pretend that this one accepted, and rejected, and dot dot dot, when you fed D, it rejected. And similarly here. Accept, reject, reject, accept, accept. Accept, accept, reject, accept, reject, reject, reject. This is a machine that rejects everything. There's going to be some Turing machine that does that. And now we got D. Maybe D, when you feed it this, I don't know, maybe it rejects, maybe it accepts this, maybe it rejects this, maybe it rejects this. But what does D do on itself? That's the question.
What's special about D?
D is the thing up here.
Oh, okay.
It's this Turing machine. What does D do when you feed it itself? You say D accepts. Sorry, what does H do? What does H do when we feed it D, comma, the encoding of D? Because here we're writing down all of H's answers. So here's all of H's answers. Now, H on DD, what does that do? We don't know, let's guess. Let's guess that it accepts, right? So H accepts DD. So now let's look at our machine. Our machine, D, when we give it input D, what does it do? It runs D on D, and we're saying H, let's say that we're in the case where H accepts. So I know that H accepts here. H says yes. When you run D on D, we accept. Now what does our program do? If H accepts, we reject. So if you put an accept here, then D on D actually rejects. So maybe we're supposed to reject here.
Okay.
Let's try that. So what do? So if H says we're supposed to reject, so H says when you run D on D, reject. So if H accepts, we reject, but if H rejects, we accept. So if you say we reject, we actually accept.
Oh, there's your answer.
Oh, sorry. I did not do this right. D is doing the opposite of whatever H says. Right? So D on M1 says
R slash A.
doesn't matter.
I don't think it
Should
does.
we be able to determine this? We should be able to fill this out. So D right here, let me think. This is what H says. H says when we run D on M1. Oh, right. Okay, now I remember. Yes, we can answer this question. We don't just make it up. So erase that. So let's see for right here, what does D say?
Accepts.
Or what does H say? I mean. So H says whether or not D will accept M1. What does D do when we feed it in M1? So D, when we feed it in M1, what does it do? It runs M1 on M1 and accepts if H rejected and rejects if H accepted.
So it accepts.
H, when we ran M1 on M1, it rejected, so D accepts. When we run M2 on M2, it rejected, so D accepts. When we ran M3 on M3, it rejected, so D accepts. When we ran M4 on M4, it rejected, so D accepts. Let's pretend that this one was actually an accept, and so D here would have rejected.
Okay.
So it's always doing the opposite of whatever this is on the diagonal. So now when we get to our own diagonal, we need to do the opposite of whatever we do. Because we're always the opposite of this diagonal. This has to be opposite that, 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 this has to be opposite that.
Okay, so it's the opposite of them.
It's the opposite of itself.
The opposite. I don't know.
They cancel.
So if we continued on our merry way, we'd keep whatever was here would be the opposite of what was here. If we continued listing out these machines. So we had a row, and that row has to be the opposite of everything on the diagonal. But the diagonal eventually crosses a row. And so you get it has to be the opposite of itself there. Which doesn't make sense. Which is another way to see how this breaks.
Yeah. Okay.
See that? So that's how we show that this problem is an undecidable problem. Can't be accepted. Weird? Yeah.
Trying to think of how that would, like an actual example of how that would happen in the real world.
An actual example of how that would happen in the real world.
Like a practical example.
Oh, of where a problem's undecidable?
Not that it's undecidable, it's that, well. I
So
understand.
one version of this in the real world is you cannot know if a program is going to crash on input. No matter how smart of a compiler no matter how smart of a IDE you build, which is supposed to tell you whether or not, hey, your code's going to crash,
Yeah. No,
it is never for sure. That's a practical example of what this is saying.
I get, well, okay.
Now, it might get the vast majority of cases, but it's never for sure. There could be something that makes it crash. And you can never know for sure that the program that the developer is building won't crash. You can only try to tell them the best you can, but there's no general way to do it. So one practical application is there's no such thing as the perfect IDE. Now, maybe there's the IDE that works for all programs that are under, 1 trillion terabytes in size. That's possible. But it's not possible in general.
You're talking about, like, it does the best it can to, like, detect that there's logical flaws in code, but can never actually guarantee that there's logical.
Sure. I mean, it can probably detect particular things, but it can't in general. So if you somehow put some limitation on it and say just these things, then yes, now you've limited it. And so then yes, there's going to be a possible way.
Right.
Even if the possible way is just checking through all possible enumerations of that thing. Which would be absurdly massive, but in theory possible. And then, yeah, there's a bunch of examples I come up with it in math. A common example is called tiling the plane. So the problem is if I give you some set of tiles, give you one where it's obviously true, like a square, is it possible to, if you have infinite copies of these things to work with, put these squared together to the point where you fill out an entire plane? In this case, the answer is obviously yes.
Okay.
You've probably seen pictures where it's like a swan together with a lion. Something weird, tiling a plane.
There's a book in there that has a picture of two swans that can live between each other.
Which one?
It's the object-oriented programming book.
Hello. But you get the idea. So that's tiling the plane. You're given these shapes. Can you ultimately fill out the plane with it? That's an example of an undecidable problem.
Depending on the shape, you're saying? If you're in
No, you can't come up with a program that in general, no matter what shapes I give you, the program can answer yes or no, will this tile the plane?
Oh, okay.
Why? I can do it.
No, you can't. And it's actually possible, it was proven, that I can give you a set of tiles that you can use to tile the plane, and it will never have a repeating pattern.
I saw this in
Crazy. Very unintuitive. You would think eventually, if it tiles a plane, then eventually it must have a repeating pattern. If you start getting a repeating pattern, yep, it'll work. But it's proven that there's tiles you can use with no repeating pattern.
I saw a video on this on YouTube. I can't remember the channel called something file. You probably
Number file?
Number file. Yeah, they talked about this.
Yeah. So, yeah, you can just look up undecidable problems, and I'm sure you'll find lots of interesting ones online.
But this one particularly, it seems like more like a situation where there's infinite recursion or an infinite while loop, or like it's like if a while loop was saying if this variable is true, well, never mind. But it just seems like it basically would run forever if it was trying to decide which one. If every time it made a decision, I don't know.
That's fundamentally what the problem is. Fundamentally, the problem is there's no way for us to distinguish between your computer's taken a really, really long time to figure it out, but it eventually will, and your computer's taken a really, really long time to figure it out because there isn't an answer.
Yeah.
That's fundamentally what the problem comes down to. Or one way you can think about it. So there's another, we're going to start with the acceptance problem in this class, and now we're going to use the acceptance problem over and over again to show that other problems are decidable, or undecidable. So we're going to use the acceptance problem over and over again, and here's how we're going to use it. I'm going to give you some new problem, and I'm going to say this new problem is undecidable. How do we know? Because if it were decidable, this would be decidable. But we know that this isn't decidable, so that new problem is not decidable.
I see.
And that's how we're going to be proving it from here on out. We're going to use what's called the acceptance problem here. But a common one that's also used a lot is called the halting problem. Now, we'll eventually prove the halting problem, but you can also just brute force prove the halting problem like this. So if you went on YouTube, you can watch a little video that proved the halting problem like this, and it will just walk you slowly through the logic of it with much better graphics than I have here.
So this isn't the halting problem.
This isn't the halting problem, this is the acceptance problem. But the halting problem, how you prove the halting problem and how you prove the acceptance problem, almost identical.
So, but the halting problem and the acceptance problem are like fundamentally the two things that aren't solved.
They're usually the two undecidable problems that we start with that we use to show everything else is undecidable.
And there's nothing other than those two.
Those are, you can use any undecidable problem you want to start with. Those are the two that are typically used.
Oh.
And it's like a coin toss between which one should we use, acceptance problem or halting problem, and it goes either way.
Huh. Yeah, it'd be interesting to see the difference.
Yeah, so if you just Googled halting problem on YouTube, you can find nice videos with nice graphics that slowly walk you through it because it's just basic logic. You can follow it just basic logic like this. They're going to create a machine that both accepts and rejects. It accepts when it's supposed to reject and rejects when it's supposed to accept. And they'll just walk you through it with a different type of machine.
I see.
And I don't know if it's easier to understand, but same basic logic, and if you can get that, it's the same thing.
Cool.
Anyways, yeah, we'll end it there since I don't have anything else written up,
Yeah.
which is too bad because we just have one more proof before we're done with the section. And it's just proving that the acceptance problem's complement is unrecognizable.